you do some sort of testing, wind tunnel testing, RCFD, to assess how much the flow will accelerate around that high-rise building and whether that can create dangerous or uncomfortable conditions for pedestrians. And then you can mitigate if necessary. Pollutant dispersion, obviously, we know there are detrimental health effects, both due to short-term exposure to high concentrations and to long-term exposure to more average concentrations. Natural ventilation, this is, Paul will talk about this a lot, so I'm just going to skip over this. But we look at it in terms of saving energy, but also in terms of occupant health and comfort. It's actually shown that when people have more of an interaction with the environment, they will feel more comfortable, they will be more productive. So that might actually be more of a benefit for building owners to incorporate natural ventilation, because people take less sick days and they work better. So it might be, in terms of the cost benefit, more important than the energy savings, actually. So these were the 4 topics that we really work on. Then topics that I think would be interested and I would like to expand in the future is looking at urban wind resources. So how can we distribute smaller wind turbines through a city to try and get more energy? And then urban heat island mitigation. Okay, so in order to kind of think about what this grand challenge is in computational wind engineering, it's interesting to look where traditional wind engineering came from. So we mainly try to look at what happens in the urban canopy layer, right? Because we're trying to understand what happens where we actually live. And in the past, this has been done a lot in the wind tunnel. So traditionally, what you do is you take an atmospheric boundary layer wind tunnel. You have these spires here that will generate turbulent flow, and then the roughnesses so that you mimic a neutral atmospheric boundary layer. And then you recreate a model of the city or the building or the bridge that you're interested in, and you measure whatever quantity of interest you're looking for. So this is the environmental wind tunnel in Hamburg University, and this is RWDI, a consultancy company. You see the scale of these wind tunnels, right? So these are really facilities that people have built and used for decades, and like engineers trust what comes out of this wind tunnel. So when CFD comes along, the first thing they ask us to do is, well, if we have to trust what comes out of the model, you have to show us that this agrees with the wind tunnel experiment. And this has really been the focus in computational wind engineering for quite a while now. It has resulted in several important model developments, like we know now how to correctly model a neutral atmospheric boundary layer in a run simulation, for example. It has also led to guidelines on how you should set up your model and how you could do validation. How big should your computational domain be to eliminate effects of blockage? What kind of grid resolution should you look at? Things like that. There are also many studies that look at a particular problem and try to say which Rand's turbulence model is better. The slightly controversial opinion I have there is that it's probably none. Because depending on the problem that you look at, depending on the quantity of interest that you look at, depending on where in the flow domain you're doing validation, you might come to a different conclusion there. We have also shown that LES can give accurate predictions, right? So we say, just do LES. However, when you look in the engineering practice, we see that quantitative use of CFD in design has been very limited. First of all, engineers complain that the turnaround time is too long. I think that is a problem that we can really mitigate. Our codes have become more efficient. We have more computational resources. It's just a matter of making them easy to use, right? The bigger problem is that engineers have very limited confidence in these results, right? And that kind of goes back to this problem. Generalizing conclusions of validation case studies is difficult, right? We can validate something on an idealized urban canyon, but that doesn't mean it's going to work in a much more specific case. Turbulence modeling is definitely the limiting factor in runs, and then if they think runs is too expensive, for sure they're going to tell you, I can't wait for 3 weeks to get a result, right? Because the architect makes a change in the building every day. So you need to get faster turnaround times. So the grand challenge here is that we would like to establish efficient predictive modeling frameworks that can quantitatively support sustainable building design and urban planning. And as we try to understand what we can do to get there, right, I think it's important to remember something, and that is the wind tunnel is a model as well, right? So what this shows you is the normalized velocity in an urban canopy as a function of height in Oklahoma City. These are the wind tunnel realizations. You see they are nicely repeatable. And these are the field measurements, and you see this huge variability, right? So what we have been trying to do, and it's what I did for my PhD as well, right, is to exactly match this wind tunnel realization here. And we can tweak turbulence model coefficients and try to get a better result for a specific case that we're looking at. But we see it might not necessarily bring us closer to reality in the end, right? So the point that I would like to make is that maybe what we should be doing is try to reproduce these field measurements, including the variability that you see in the field. So in order to do that, I think we should leverage advances in computational resources, uncertainty quantification, and data assimilation so that we can actually address validation with field measurements. So to me, uncertainty quantification has really been the starting point, so I'm mainly going to focus on that. I'll show you some new research we've been doing on data assimilation at the end as well. So what is uncertainty quantification? The goal is to quantify and eventually reduce the uncertainty in our simulation output, right? So experimentalists are supposed to give error bars on their experimental results. Well, we as computational scientists should maybe start thinking about doing that as well. Uncertainty quantification is inherently linked to validation, in particular when you're using field measurement, because there is no way that in field measurements you're going to be able to accurately quantify your boundary conditions or all the sources and sinks that are in your computational domain, right? I think doing this, even though it's very complex, is important because it is the only thing that is going to reflect the full complexity of the problem. So what does this look like when we actually plot the results? When we look at our flow field, instead of trying to make this one deterministic prediction of a velocity vector at a location, we're going to put some confidence interval on that. In terms of concentrations, just the same thing, right? We want to get error bars. Okay, at this point, I quickly want to make the distinction between errors and uncertainties. We talk about errors as being associated to the translation of a mathematical formulation into a numerical algorithm or a computational code. So this is a mathematical problem, right? And you have two categories. You have acknowledged errors like convergence errors or discretization errors. And then you have unacknowledged errors that might be user errors or bugs in your code. If you do comprehensive verification, then you can characterize these. On the other hand, uncertainties are associated to the physical model choice and to the input parameter specifications, such as your boundary conditions. This is much more strongly connected to validation, right? So errors are a mathematical problem. This is much more a physics problem in a sense. Then in uncertainties, we again distinguish between two types. So you have aleatory uncertainties that are the physical variability that is present in the system that you're analyzing. These aleatory uncertainties, they're inherent to your system. You cannot reduce them. You're not going to get rid of them. You can characterize these using probabilistic approaches. And examples are for the variability in the inflow velocity, magnitude, and direction, which I'll talk a lot. You could think about variability in stability conditions, pollutant sources, things like that. Then you have epistemic uncertainties. Those are potential deficiencies due to assumptions or simplifications that you make in your model. So these are uncertainties that you can reduce, right? Instead of doing a run simulation, I can do an LES simulation, and I will have reduced my epistemic uncertainties. They're not as easily characterized using probabilistic approaches because often they involve a bias, so it's more tricky to do that. A lot of work in UQ, though, is to try and actually do this, to cast epistemic uncertainties in a probabilistic way. Examples are a turbulence model, a mixing model, radiation models, also geometrical simplifications. So this is kind of very general. When you think about this in terms of urban flow simulations, I like to make the distinction more like this because it also kind of separates the problems and how you address them. So the first one are influences from the larger scale environment that will define the boundary conditions of your domain. So for example, the flow conditions around a building or city, right? If I'm interested in the natural ventilation in this building, I could model only this building, but it's really going to matter whether it's in this environment or that environment. So we can characterize these uncertainties either by going in there and doing field measurements, or we could do a simulation of that larger scale problem and couple the two. This you can do propagation using non-intrusive statistical methods, so you just run a larger number of simulations. Then the second is uncertainties in models for physics that we're not resolving in our simulation. And this is kind of challenging from a physics point of view to quantify, right? So we're thinking here about turbulence models, turbulence scalar flux models. And if we want to get an understanding of these uncertainties, we're going to need input from high fidelity simulations or from lab experiments that measure the quantities that we're modeling with high accuracy. There, so as I said, UQ kind of focuses on casting these into statistical or probabilistic frameworks as well. What we have been trying to do first, because I think it might be more tractable, is to do a propagation using interval approaches. So instead of trying to predict the probability of a quantity of interest, we're just going to try and predict a minimum and a maximum of a quantity of interest. Okay, so just kind of to summarize this graphically, right? So we have uncertainty because of variability in flow conditions, uncertainty because of reduced order model outputs, and then we need to propagate these uncertainties by running a larger number of deterministic simulations so that we can get probability distributions or bounds for quantities of interest, and then we do validation with field measurements. So the first type of uncertainties we characterize with field measurements are simulations of the larger scale. So this is kind of a multi-scale problem. At the bottom part, we characterize this with high fidelity simulations or lab experiments, and this is much more of a multi-fidelity problem, right? Often we do this on subsystem problems because we can't do these high fidelity simulations on the real expensive problem, right? If we could do that, we should just use them here and we would get rid of our model uncertainties. Then lastly, I think it's very important in our area that we think about application-specific problems, because what matters most here is really going to depend on this quantity of interest that we're trying to predict. Okay, so let me go into the validation case studies. How far along am I, Nick? Because, okay, because my timer started way earlier. Okay, so pollutant dispersion in Oklahoma City, and here we quantify uncertainties in the inflow boundary conditions using either field measurements or weather forecasting models. So we use this joint urban 2003 field experiment, and we look at one of the intense observation periods. So these were half-hour periods where they did more dense measurements. We have a dominant wind direction from the south, so that's in this direction in this plot. And there was a 30-minute continuous tracer release, like in the downtown area, somewhere in that area here. They have velocity measurements at 25 locations and tracer measurements at 10 locations. This study focused on providing a prediction with uncertainty intervals for the mean velocity and the tracer concentration at the measurement stations. I'm going to focus on the tracer concentrations here only, just to save some time. So the setup of our simulation, we use a run simulation, a k-epsilon turbulence model. We picked the most basic model because we also used this study to do the turbulence model UQ, which I'll show at the end of the talk. The domain size is based on these guidelines that I mentioned before that were developed, that was in the COST 732 project. We have 7.4 million hexahedral cells, and then we use the inflow conditions for a neutral surface layer. The experiment was in near neutral conditions. So we have a log law for the velocity here, then turbulence kinetic energy is friction velocity squared over the square root of c mu, which is a constant in the turbulence model. And epsilon is from equilibrium between production and dissipation. When you impose this in a general purpose CFD code, what you will see is that if you impose this logarithmic profile, and you always have this upstream region in your computational domain, right? Because the boundary condition needs to be far enough from the first building. That profile actually starts to develop and you get something like this. So if you're interested in what happens at this level, at pedestrian wind comfort, for example, and you already have like a 30% increase in velocity here, that is purely because of numerics and modeling, you're not going to get an accurate result, right? So if you take any general purpose CFD code, you actually need to modify the WAL function to represent that correctly and make sure that you don't initially get this development of the profile already, so that by the time you hit the first building, you still have what you intended to have. So these boundary conditions require specifying a friction velocity and a roughness height, right? So the friction velocity, you can get that if you have a reference velocity at a reference height, and if you have your roughness height, you calculate that. So we're going to consider a roughness height as an uncertain parameter, the reference velocity at the reference height, and then also the wind direction. So we have 3 uncertain parameters. And in the first version of this inflow uncertainty quantification framework, we just used field measurements because we had a sensor that was right at the inlet of our computational domain. For the roughness height, we relied on an image roughness map that we digitized to fit a distribution to the roughness height. I think the more interesting part is here, where we look at the wind magnitude and the wind direction. So we have a time series at our inlet of the domain for the magnitude and the direction, and we can really just convert that into a PDF, right? So this was the first thing we did, and we thought, wait a minute, this is probably not the right thing to do, because you see a lot of fluctuations here, and we're actually running a RANS model, so part of the turbulence is represented by our turbulence model. So at the inflow, the turbulence is this friction velocity squared over the square root of c mu. And we can actually filter that measure signal to remove the smaller scales that are associated with this modeled turbulence kinetic energy, so that our inflow variability represents the larger scales only. If you assume there's no correlation between the small and large scales, you can do that pretty easily, both for the wind direction and the wind magnitude. So when you do that, that looks like this. So you get this filtered signal now for both the wind magnitude and the wind direction. And you get these PDFs that have a smaller variance, right? Especially for the wind direction, we have a variance that is reduced by quite a bit. I'll show you results for both of these distributions just to get a sense of what the importance is of specifying these PDFs. Okay, so in summary, we have 3 uncertain inflow variables: the velocity magnitude, the velocity direction, and the roughness length. We have probability distributions for all of these, and they will define the boundary conditions for our domain. And then for the velocity direction, we basically just changed which planes are inlets, which planes are outlets, to vary that. So how do we do the propagation? We generally use non-intrusive polynomial chaos approaches. And they rely on the fact that you can write any quantity as a polynomial expansion, right? And what you do here, so this quantity, we don't have time, but it could be a function of time, space, and then random parameters q. And you write it as a summation of deterministic coefficients, and then here a polynomial basis that is a function of the random component of the solution. So what you do here is you effectively separate like the spatial temporal dependency that is deterministic from the random component. Right? So why is this interesting? If we think about this, just to make it more simple, for a single continuous random variable, then we can use 1D polynomials that are orthogonal with respect to the density of our random parameter here. And then we index them so that the polynomial with 0 index is equal to 1. And then it follows that the expectation of this expansion, which you have written like this, you can take the 0, k equals 0 term here, and then all the other ones here. The coefficients are not a function of the random component, so they can come out of the expectation. This expectation is 1, right? And this expectation is the integral of this polynomial multiplied by the density, and they are orthogonal, so all of these disappear. Right, so my expectation is really just equal to the first coefficient in my polynomial expansion. Similarly, you can show that the variance is just equal to the sum of all the other coefficients squared in the expansion. So the coefficients can then be calculated using numerical quadrature. So that also means that you kind of have a convergence, right? The more samples I can take, this is eventually going to converge to the best expansion, or to the real mean and variance. If you want to have the PDF, so this is good to calculate expectation and variance, but if you want to get a PDF and a 95% confidence interval, then you actually need to reconstruct this expansion, and you just sample it with Monte Carlo, which is really fast. Okay, so the results that we get for the concentration field, you see here a map of Oklahoma City. This is the source, and then we have 9 sensors distributed, but this one was not operational during our experiment. So we have these 8 sensors in the downstream region. So this is non-dimensional concentration for the different stations. The black crosses are experiments, and then we have two results from the UQ study. The magenta one is the one where we use the large variance, and then the blue one is the one where you use the variance that only corresponds to what we call the larger scale inflow variability. Okay, so first of all, I was super happy seeing this results because I ran a deterministic simulation for this during my PhD, trying to match this, and I never even attempted to publish that because the result was so bad, right? So here you see that we actually get a pretty good prediction of that mean concentration. If we look at the 95% confidence interval, then we have 6 of our 8 measurement stations that are within that confidence interval when we use the total variance, and 5 when we use the reduced variance. Where we do not get it, it's actually in the regions where we're looking at pretty low concentrations. And here, the smaller inflow variance really only just misses it by a little bit, right? Definitely, the choice of these input PDFs is important, not so much for the mean, because their means were the same, obviously, but it will reduce the variance if you have a lower variance in the input parameters. So really thinking about how we can correctly set these probability distributions for our input parameters is one of the important challenges in UQ, right? It does give you a consistent indication of the points that have a larger uncertainty and a smaller uncertainty, right? No matter where I look, this one has a larger uncertainty than this one, both for the magenta and the blue one. And for an engineer, that is already very useful information, right? You know where in the flow domain you can trust your model better or not. The other interesting thing that you can do with this is you can do a global sensitivity analysis. So what you see here is we didn't only look at the measurement stations here, but we basically made a map of the variance at all the locations in our area of interest. So the source is here, and you see that you have the larger variance here, and then as you move downstream, it decreases. What you can do now is you can calculate Sobel indices. And what a Sobel index is going to do, it's going to tell you what portion of this total variance is caused by the variance in one of your uncertain input parameters. Okay, so they should sum to 1 in the end, right? So what you see here is how much of the variance is caused by my roughness height, how much is caused by my velocity at the inflow, and how much is caused by the wind direction. When you interpret these, you always need to interpret them in conjunction, right? I have very little variance here, so I shouldn't really be thinking about what happens here. It's not relevant. However, if we look at the regions of the larger variance here, we see that most of that is caused by the inflow wind direction. And that makes a lot of sense, right? Because we have this large-scale meandering in the flow that you see. And that might determine whether the flow in a street canyon is going to the right or to the left. So when I do my deterministic simulation, I get one flow solution, and the pollutant is going to go right or left. And if it's wrong, I will completely miss what was measured in the experiment. Now, when I do this kind of study, I actually reflect that meandering of the wind because I will get both solutions and I will average that out. So definitely representing that uncertainty in the wind direction, I think, is essential. You see that there is definitely some non-negligible contribution of the reference length and the velocity as well. The roughness length and the velocity as well. Okay, so that was based on the field experiment. Then we said, okay, what if we don't have experiments, right? Can we use weather forecasting models to try and do this? So we use WRF in this case. A lot of people have looked at coupling WRF with a CFD code, just interpolating the solution from one domain on the other. There are lots of challenges here. The resolution I have in my inner domain is 1 kilometer. My domain was only 4 kilometers wide, so I have 4 points, and I have to come up with some sort of interpolation. A bigger challenge is that you have an incompatibility between what WRF does and what the CFD does in terms of turbulence and wall modeling. So I'm going to have that same problem that I showed you before. I get a velocity profile out of WRF, but when I put it in my CFD domain, it changes immediately to match the model that I am, the equations that I am solving. The other problem is that you have uncertainty in these WRF predictions, right? Weather forecasting is definitely not a problem that is solved today. So what we decided to do is, instead of trying to do this direct interpolation, we said, okay, we're going to use an ensemble of WRF simulations, which at least gives us a representation of the uncertainty in the weather model, and build PDFs that are equivalent to what we did before when we did our field measurements. Okay, so we take the point that is closest to our inlet domain, we ran in this case 8 different WRF simulations. This is the velocity that you get over time. This is an unsteady run simulation, so we basically have to do the opposite of what I did before. So you get a velocity variation over time, but you also get a turbulence kinetic energy over time. So we need to impose fluctuations on here to get like the real signal that we want to have. And then we need to subtract again the turbulence kinetic energy that our runs model does. That way we actually make the two compatible. Okay, so after you do that, you can get probability distributions, and here I plot them as CDFs because it's a nicer way when you do ensembles to actually show you the spread in the probabilities. So the blue lines are all the different realizations. The magenta is the ensemble, the black is the experiment. So we're really not doing that bad. Definitely most of the models are over-predicting velocity by quite a bit. Apparently that is something that is a known deficiency in this model given the specific conditions that happened at the time of the experiment. For the wind direction, our ensemble definitely encompasses the experiment, but the spread is quite a bit wider in the wind direction. If we use this ensemble to do the same prediction as before, what we see is that we again get a pretty good prediction of the mean, but this scale is much larger than on my previous plot. We get a much larger variance here than what we had before. And that is really because that variance in the wind direction in this case was much larger than what we got from our experimental data. You can also look at the variability that you get in your prediction of the mean over the different ensembles to get a better idea of the uncertainty. And we see that that is actually not too bad, right? So even though there is a lot of uncertainty in these WRF simulations, and we might have to think more about how we correctly transport that to our CFD simulation, this is not a useless prediction, right? So it's definitely a method that could be helpful. Yeah. Okay, the Stanford engineering quad. I'm half an hour. Oh, I'm doing really good. I should slow down. Okay, we thought, what if we get lots of data in urban areas, right? And we just have flow measurements in our urban canopy. Can we use those flow measurements to do uncertainty quantification of our inflow boundary condition? We started modeling the campus for the very simple reason that it's not always easy, but it's much easier than working with a municipality to like go and set up sensors all around, right? And we can kind of just do it and then ask for forgiveness later if they don't agree. So we have, what this plot looks like now is that we actually do this comparison between our quantity of interest and field measurements, and then we go back and we do data simulation to better characterize this variability in the flow conditions. The paper that I cite here is really just on the development of the experiment. We have one under review right now on the results as well. So this is our campus model. We have the science and engineering quad here. This is the Y2E2 building. That's where our department is. We basically model all of the buildings within an 800-meter radius from our building. So this is our computational model here. Again, this is where our building is. We have about 24 million cells here. In the Oklahoma City model, we didn't do tree modeling, and we could really see that that might affect the accuracy of our predictions. So here we do parse modeling for trees as well. The boundary conditions and solver settings are all very similar to what we did for Oklahoma City. So what we wanted to do is just really compare what do people do today in the engineering practice, and how could we improve that when we actually do data simulation. So what people do in practice is, okay, they want to look at the wind climate in this area. They're going to look for the nearest weather station. They're going to take that weather station data, usually it's hourly average data, and use that as boundary conditions for their deterministic simulations. And they'll run a number of different wind directions. Said, okay, what if we have sensors in our urban area, right? Can we use, and we decided to use an ensemble Kalman filter. It's very easy to implement, to infer probability distributions for our inlet conditions from the sensor data. I was very happy that you gave an introduction to data simulation yesterday. So I'm gonna do even shorter. So what we do here is we have our forward model, right? And we take a number of realizations of so we draw a number of realizations from our inflow distribution, which is a prior distribution that is non-informative. We run a number of realizations, we compare predictions to observations, and based on that, we update our inlet and we go back. The ensemble-Kalman filter is an iterative procedure, so you run this until you converge on what the probability distribution for your inflow should be. Obviously, this involves running your forward model a lot of times. So what we did here is we again build like a polynomial chaos expansion, so we build a surrogate model that we construct based on 63 CFD simulations. So this is actually something that is pretty cheap to do in the end. Okay, so our weather station, so this is again our area of interest. Our weather station is here. We look at 3 consecutive days of measurements here, so you see hourly average data of velocity, magnitude, and the direction. We have radiation and temperature as well, but we're currently not looking at that. And then we have our sensors, where we can look at the probability distributions that we get over an hour as well. So in terms of the results, we have 6 sensors here. The blue line that I show you is the experiments. Then the shaded area on top of that is the 95%. So we average them every hour, and we show you a 95% confidence interval as well. Then we have our prediction from the Bayesian inference. So you can clearly see these 2 sensors are the ones that we use for a simulation. These are the ones that we use for validation. But overall, like again, we were pretty happy to see this prediction. And we were even happier when we compared that to what we get with just the deterministic simulations. So this shows you the average error over these validation sensors. And you really see that with this very simple Bayesian inference process, we can get something that is really much better than the state of the art that they are using in the design practice today. And I think that's one of the messages, right? We're not going to solve this problem today, but we can definitely make incremental improvements that are relatively easy for these people to implement and do better design. Okay, these were my 3 inflow uncertainty cases, and then I'm gonna totally shift gear and talk about turbulence model form uncertainties, where we're trying to develop this interval method. So what we do here is we want to get an idea of what the uncertainty is due to reduce our model outputs. And in our case, we used high fidelity simulations. And because we cannot do a high fidelity simulation of Oklahoma City, we can, but it's extremely tricky. We do this on a single building. So we have DNS data available here. You see the flow on the symmetry plane from the DNS, and then this is what we get from a Run's K omega SST model. So really, there are so many studies that have looked at this. I kind of did my whole PhD on the flow around like a single building. It is probably the most complex case to predict, because getting this wake length right and getting the separation on the roof right is something that is incredibly difficult with a Run's model. Run's models were not developed to solve this kind of bluff body flow problems. You see turbulence kinetic energy here, so you see we completely underpredict the turbulence kinetic energy in the wake as well, which might partially explain why we have that very late reattachment here. Okay, so let's start from the basics, right, and think about Reynolds averaging. When you do that and you write your Navier-Stokes equations, you get the Reynolds stresses in here. There are hundreds of models available, but what is mostly used in the engineering practice are the models that are based on the Boussinesq hypothesis, so they use a linear eddy viscosity assumption. When you look at that assumption, you see that you write your Reynolds stress tensor as an isotropic part, and then an anisotropic tensor that is a function of a turbulent viscosity and then the rate of strain tensor. So this is really the first important assumption you make, but then you need to get this turbulent viscosity. In the K omega model, that's done like this, and then you write 2 transport equations for K and omega. So there are 2 things, right? You have this main assumption of this isotropic turbulent viscosity, which assumes that the Reynolds stress tensor and the rate of strain tensor are aligned. And you have all the secondary assumptions that come in here, how you compute mu t, K and omega, what your model constants are in the equations, things like that. Traditional sensitivity studies will look at model influence often by just using different 2 equation models and by changing model constants. So what you're doing here is that you're addressing these secondary assumptions, but you're not at all looking at the influence of this assumption. So if you really want to get an idea of what the uncertainty is because of your turbulence model, you really have to look at what goes wrong here in that main assumption. Okay. So this methodology was something that was developed at the Center for Turbulence Research when I was a postdoc there. So there was a PhD student working on that, and then I did quite a bit of work on it as well. The idea here is that you introduce a perturbation to your Reynolds stress tensor. So you have your original model prediction and you add a perturbation on top of that. And the way we're going to define this perturbation is by decomposing the tensor into its isotropic part and then the anisotropy tensor. So we have the magnitude up front here, and then we have the anisotropy tensor where we have the eigenvalues that indicate anisotropy, and we have the eigenvectors that indicate the orientation of the tensor. So let me... And the nice thing about this is that for the anisotropy, you have the realizability constraints that you can use, right? We know that the turbulence, the Reynolds stress tensor needs to satisfy these realizability constraints, and you can plot these in an invariant map or in a barycentric map. So this is the barycentric map, and when you compute the eigenvalues of the Reynolds stress tensor, you can do a linear mapping, and the coordinates should end up being in this triangle. These are the limiting states of turbulence. You have one component turbulence, two component turbulence, and then fully isotropic turbulence. So what we can do is, if we think about this intuitively, we might think that these might actually limit our predictions as well, right? Because they are the limiting states of turbulence. So we could take our original Reynolds stress tensor prediction, look where it is in the map, and then make it more one component, more two component, or more three component. There is an additional reason why we might think that these corners give us limiting behavior. So the only term that we actually know exactly in this model is a production term, right? We know it's the product of our Reynolds stress tensor and our velocity gradient tensor. And you can actually show that you're maximizing production if you go towards the C1 corner here. If you go towards the azotropic corner, production is equal to 0. Okay? So what we're going to do is we're going to do these perturbations in the eigenvalues and then perturb the amplitude by calculating our production with the perturbed eigenvalues. You can also show that you get, in terms of the orientation, if you go to C1 and the rate of strain tensor and the Reynolds stress tensor are aligned, you really get the maximum production of all. So we can keep our original model alignment to look for maximum production, and we'll get 0 production in the isotropic corner without doing any changes to the orientation as well. Okay, so what does this look like when we do that on our single building? We have a DNS prediction, we have a RANS prediction, and then we have our 3 perturbations. This is towards maximum production, C1. This is towards minimum production, and this is to the C2 corner, which gives something in between. We never perturb all the way to the corners because it's kind of unrealistic to go all the way to the limiting state. So how far you go is a little bit of an open question, but we have shown that it behaves monotonically. So the more we go to the corner, the more we increase these bounds in our predictions. So you see that maximum production decreases the length of this wake, and minimum production actually increases the length of this wake. So we do get this bounding behavior. Looking at a few quantitative profiles here. So we look at a profile upstream of the building on the rooftop and then in the building wake. You have the SST model, are the crosses here, the DNS are the circles, and then we have our bound on the prediction. So it's really not behaving badly at all, right? We do get some sort of bounding behavior, and we can get some sense of where the biggest uncertainties are because of the turbulence model. We've tested this in a lot of cases, and it works surprisingly well in a lot of cases. I think one of the challenges here that this is really model development, right? So we are going to have to validate this over a broad range of cases to really believe that it's robust. Okay, we did apply it to Oklahoma City. There is really not a way to validate this well, but you do see something interesting, and that is that it seems to indicate regions where we have very small uncertainties because of these turbulence model assumptions, and regions where these uncertainties are much larger. So again, for an engineer who is running a RANS simulation and is like scratching his head, like, how much can I trust this result? This is pretty useful information, right? The other thing you can do now is you can kind of compare, if you visually think about this, right? Inflow uncertainties were much more important in these locations than turbulence model uncertainties. On the other hand, here they're probably almost equal in magnitude, right? So you can start thinking about this balance, like which uncertainties are more important and where should we really focus our research efforts to improve our predictions as quickly as possible. Okay, so a summary and outlook. I'm gonna summarize a little bit and then try to show a little bit of a path on how we can realize our grand challenge. So we've shown that inflow uncertainties are important. You can characterize them in different ways. If you have field measurements at the inflow, you could use weather forecasting models or data assimilation from sensor networks. I think the exciting thing about this is that it actually also improves your predictions, right? So to me, going forward, this is really something that we should think about a lot more. Even when you don't do this though, your forward propagation will give a prediction for a mean with 95% confidence intervals. And if you're going to do validation with experiments, especially field experiments, this is a way of getting a meaningful validation, right? Doing a one-on-one comparison is almost always going to lead you nowhere. In terms of turbulence model form uncertainty, so we have that interval method that perturbs turbulence towards the limiting states. I should say we're also working on this for mixing models, so that might be more of interest to a lot of you in this audience. It does provide limits on our predictions, and we have done validation on a number of subsystem problems, but it remains a challenge to really believe that this is robust when you go to our more complex models. So there's a bit of work to be done there. Then these are some other applications that we are looking at. So we're looking at natural ventilation, which Paul is going to talk about a lot. So I'll just give you a very quick summary. Here we're trying to predict the temperature in our building. We have a natural ventilation night flush. So we're doing both modeling and measurements in the building. We're doing a hierarchy of models as well. I'll touch on that a little bit later again. And then we're looking at model predictive control. So during the during the operational phase of the building, can you use model predictive control to get the most comfortable conditions? We're looking at ventilation in slum housing in Bangladesh. Pneumonia is the #1 cause of death in children under 5, and it's very prevalent in these slum housing in third world countries. There is some evidence that there is a link between the occurrence of pneumonia and whether you have sufficient ventilation in a home. So we're working with Steve Luby there. We're doing some modeling. We have measurements in the field there. And then there will be a clinical study in the end to try and really show that link. If we can do that, the idea is to translate this into health recommendations. We're looking a lot at wind loading. NSF is kind of interested in that right now. So this is both a regular grant and my career award. Predictions for a single building and then on buildings in an urban area as well. So in terms of the grand challenge that I started with, right, I think the really important thing here, and this is modified from the book that I used to teach my uncertainty quantification class, is to take all these different components, right? We have lab measurements, field measurements, reduced order models, and CFD models, both runs and LES. And we've done quite a bit of work on like, how do you quantify uncertainties in each of these separately, right? But we need to bring that together, and I think uncertainty quantification, data assimilation, and probably also machine learning will be instrumental tools to do that, so that we can get predictions for quantities of interest with confidence intervals as well. In terms of UQ, there is a very long list of smaller challenges. I kind of highlighted the ones that I am most interested in right now. So for inflow uncertainties, for weather models, you can wonder whether an ensemble approach is robust. Data assimilation, right now we did these 3 days of predictions for we had measurements. Can we use past data to inform like yearly predictions that people are really interested in when they do design? Turbulence model form uncertainties, is this method robust? There are definitely data-driven methods out there, but you take data from a specific configuration and then do some sort of inference, and it works really nicely in that configuration. But can we somehow generalize that? I think a very interesting approach is multi-fidelity methods. So you run a lot of run simulations and a few LES simulations, and you combine that information to try and get to an accuracy that is similar to as if you would have run a lot of LESs. It's very challenging though when you go to more complex problems. So the question is whether this will be adequate and affordable for our problems. A big one that I didn't touch on is geometric uncertainties, the accuracy of building locations and geometries. I think there people are thinking a lot about digital twins, right now mainly for buildings. So you have a digital building and you're continuously running models and you have all that information. In the bigger scale, you can think about a digital twin for a city where all this information would be available to the research community and policy makers. Details in the representation of buildings is another challenge. A lot of other processes, some of that was touched on this morning, so adequate models for vegetation and traffic. I think going there to probabilistic models would be very interesting because we know we can't get that answer right either, so we should get some sort of uncertainty out of these models. And then, yeah, including temperature and moisture effects is something that we haven't started to do, and it's definitely important for some problems. So that list is long and incomplete, probably, but I think there is hope, because uncertainty quantification really offers you a framework to identify these dominant uncertainties, and that is going to allow us to focus our research efforts on the uncertainties that matter most. In addition, uncertainty quantification provides a very natural pathway to data assimilation. And I do believe that that might be our best opportunity for improving the predictions in the near future. Of course, that comes with a data grand challenge that was also mentioned earlier this morning. Obtaining quality control data, even if it's not very accurate, we do need an error estimate, that's essential. And then building platforms to share the data. It is surprisingly difficult to get data from the municipality. Like even just getting data from Palo Alto is an extreme challenge for us. The last thing that I said is they need to be efficient, right? And I think there we need to think about having modeling frameworks that incorporate a hierarchy of models for different purposes. And especially when you think about natural ventilation, I think this is something that we can do pretty quickly right now. In the initial design phases, designers need simple and fast models with uncertainty quantification so that they can decide what are robust solutions, like which path should they take when they start refining the design. In detailed design phases, they can start using more expensive models that either inform parameters in that simple model or that provide more accurate estimates of your quantity of interest directly. And then you can use these models in the operational phase, right, where you can inform them once you build the building and you start gathering data. You can inform them by that data to improve them, and that can support robust and efficient operation of your buildings as well. So that was all I have. I'm going to leave this slide up as a starting point for questions. Thank you.
Questions?
Thanks for the talk. That's a really cool thing to keep in mind with all of the modeling that everybody's doing. Kind of back to a fundamental question I have with when you're working with field measurements and you're fitting these PDFs to them, it seems like there's probably a lot of uncertainty in that and dealing with natural environments and stationarity concerns and things like that. How is that something you're keeping in the back of your head as you're preparing to move forward with that PDF from the field?
So, I mean, there are two things here, right? First, the stationarity is a problem, right? But by actually doing this PDF, we're kind of taking that into account because we're going to have like this, you have both the small scale oscillations and then a larger scale time variation, right? And we kind of filter out the smaller scale ones because we say those are represented by our turbulence model. So these larger scale ones are in the PDF. So we are going to represent that time variation in there. The problem that we have is that the other thing we could do is run an unsteady run simulation, right? But then we are trying to get like an exact time like variation, the time signal, which is going to be much more difficult than getting that PDF, I think, unless you have the actual measurement. So what we lose is the possible hysteresis, right? We don't have any of those effects. What we want to do, we haven't done it yet, is run an unsteady runs and compare it to what we did to kind of get a sense of how important that is. But yeah, my sense would be that this is a second order effect. It's not like the most important one. With what we do, we get that meandering of the wind represented in the solution, and I think that is very important. The other thing you referred to, I'm pretty confident that what we measure is what we measure, but there are lots of other things that we don't know, right? We measure at one point, and we actually have an inflow boundary condition there. So you can start thinking about making this approach more complex and putting a non-uniform boundary condition. I don't know if that's gonna help us much. Like, often making something more complex is not necessarily going to improve things that much. It's worth looking into. But yeah, from an engineering design point of view, you want to try and keep these things as simple as possible. So if we can get the first order effect represented by what we do, I think that's the most important thing.
Thank you, Catherine, for a very nice talk. So this is important in the turbulence model, right? So you started, one of your bullet points was, is any RAND's turbulence model any better? You said none, right? And then during your uncertainty quantification, I noticed you used Mentor's K omega SST. Clearly that does well with flow separation. So is there an implicit bias already there that you have evoked in the analysis?
So we can run this uncertainty quantification with any turbulence model. Yeah. We have done it. So we did this study for a wavy wall where we used both a realizable K epsilon and SST K omega model. The bounds that you get are obviously different, right? Because you start from a different point in the triangle when you do the perturbation. But in both cases, it gives you bounds. And usually they bound the DNS prediction, and they definitely bound the initial runs prediction as well. So the bounding behavior is consistent. Yeah. Does that make sense? Yeah.
Thanks, Catherine. Very nice. Just a quick question. How do you decide where to put your field sensors? So for the New Orleans and for the Stanford experiments.
Yeah, so Oklahoma City, we didn't do that experiment.
Oklahoma,
that was done in 2003 by a big consortium. Stanford, what we did is we initially ran CFD simulations and we tested our data simulation method. And we looked at the errors that we get depending on where in the flow our sensors are. And what you see is that definitely you need a sensor on rooftop, which is totally obvious because that's going to correlate most with the inflow wind direction. But then additionally, you probably want a sensor at pedestrian level as well, because that's going to give you some information about the vertical variation. You do not want to put it in a street canyon where the flow is predominantly going to go in one direction, because that's not going to help you infer much. The problem will be ill-posed. So yeah, we used CFD simulations to try and understand where to put them.
So very nice and exciting to see the importance also in these problems of data simulation. So one question is, you were talking about surrogate modeling, which is very important topic because normally it's very expensive to do Kalman filtering. So if you give him more details about that and how expandable to other communities could be.
Yeah.
And then the second one is, I have seen your comparison with the data for Oklahoma City, and you said the two sensors were out of the band, but you didn't put the error on the measurements.
Yeah. It's because we didn't do that because we're comparing means. I think if we, and the error they cite is kind of small. Like the error they cite for the measurement sensor is small. And then what we could do is take the time series and put a confidence interval, but we decided to just compare the means in this case. We've done some other analysis, but we never really went into much detail. For the surrogate model, so we use this polynomial chaos approach that I showed you. And we use a quadrature-based method. So it depends a little bit on the case. Yeah, this is kind of complex because it goes into the... I think the first thing is what we did works really well if you have a relatively small number of uncertainties, because we use numerical quadrature techniques. And if you have a high dimensional space, you need to calculate an integral over a high dimensional space. So you have a problem there, right? There are techniques to circumvent this. So there are techniques that instead of calculating the coefficients with a quadrature-based method, they use just the least squares method, and then they try to find which polynomial terms matter most. You lose the convergence thing there. With numerical quadrature, we know if we add points, we're converging. With least squares, you don't necessarily know anymore. And there are some least squares approaches to try and identify which are the most important directions in your uncertain parameter space as well. There is a lot of research in this area, yeah. Because we have relatively a small number of uncertainties, we use a simple quadrature-based approach.
Yeah, sorry, you might have talked about this, but is the wind speed PDF independent of the wind direction? As in, do you get faster speeds from certain directions?
We looked at the correlations, but they're not that high. So it really, because we thought that might really be a problem. So I had like a graduate student look at that once, and that kind of went nowhere. It didn't look like there was a significant correlation. Yeah.
Okay, great. I think we'll stop there. Thanks, Catherine, again.
Yeah.